Hello! In this video we will carefully work through a problem involving forces, using what is known as a force diagram, or also as a free body diagram. The example you see will be relatively simple compared to later problems, but the basic 5 steps that we will follow here apply to even the most complicated of problems. So the most important part is to understand the process. As you can see here, we have 2 astronauts floating in the blackness of space. In order to maneuver, they have jetpacks, which exert forces. Those forces, in turn, accelerate the astronauts in a certain direction, which gives them control over where they go. In our example, we have 2 astronauts who are each firing their jetpacks in a different direction. The astronauts are connected by a blue rod in such a way that the 2 of them move together. This means that they will have the same acceleration. Now, let's say we are given the masses of the astronauts, and we are given the value of the forces that their jetpacks produce. In the vector on the right, we are given the force vector as an x and y component. In the vector on the left, we are told the magnitude of the vector and its angle relative to this line. These are 2 different ways you'll see forces given to you, so for this problem, I'll give you one of each. The thing we want to know is, what will be the acceleration vector of the 2 astronauts? Recall that they will have the same acceleration. Now, the very first step in any problem like this is to make a simplified diagram of the situation. You're going to want to draw this scenario on a piece of paper so that you can write things on it, but you aren't going to want to spend a lot of time drawing astronauts and fire just to solve a physics problem. Rather, you're going to want to make as simple a diagram as possible. Also, a simplified drawing has the advantage of cutting out any extra information, so that solving the problem will be less confusing and perhaps easier. In our case, the 2 astronauts move as one unit, so we can actually draw a single rectangle to represent both astronauts. The mass of this rectangle is the combined mass of the astronauts, which is 80 plus 70 kilograms, which equals 150 kilograms. Great, that is the end of step 1. We have taken this complicated drawing of astronauts and fire and simplified it into a single rectangle. Now, the second step is to show all the forces acting on the object. In this case, you've been told exactly what the forces are, so we just need to copy those onto the diagram. Whereas before we had each force acting on a different astronaut, in our simplified picture the 2 forces act on the same combined object. You should know that in the future this step will be a bit more difficult, since you won't be given all the forces, but will instead need to think about what forces act on an object and in what direction. Next is step 3, choosing the directions. We have to choose a direction for what we will call x, and that determines the direction of what we call y, since x and y need to be perpendicular to each other. The standard assumption is that x is positive directly to the right, and positive y is straight upwards. However, you can choose the directions to be whatever you want, and sometimes you'll find it advantageous to choose a tilted set of directions, or perhaps a flipped one. But in our case, since we were already given a force vector in terms of the default x and y directions, we should probably stick with the normal directions. While we're on this step, we should take this vector, which is given as an angle and a magnitude, and turn it into x and y components. This could also be done later if we wanted. To find the x component, we recall that cosine of an angle equals the adjacent over the hypotenuse. In our case, that would create this equation, since the adjacent is the x component and the hypotenuse is the magnitude, which we are given. Solving for the x component, we get this expression. Now, if we plug the values in, we find that we get a positive x component. However, it's obvious that x should be negative since the vector points to the left. The reason we got the wrong sign is because we are working with an angle measured from a line going to the left, not going to the right as is the proper convention. This is fine so long as we remember to insert the negative sign where appropriate. Alternatively, we can realize that if the given angle is 30 degrees, then the angle measured from the correct line is 150 degrees. If you plug that into the equation, you will get the same value with a negative sign. Similarly, sine of an angle is the opposite component over the hypotenuse, which in our case means the y component over the magnitude. Again, we solve for y, and find that y equals the magnitude times the sine of the angle. If we plug this into a calculator, we get this result, which is positive. We can agree that a positive number is correct, since the force is directed upward. The fourth step is to set up the F equals ma equation for each object, in each direction. In our case, we only have one object and 2 directions, the x and y directions. So we will only need to set up 2 equations. Let's start with the x direction. Newton's second law tells us that the sum of forces acting on an object equals the object's mass times its acceleration. So first, let's find out what the sum of forces in the x direction is. we have a positive 34.2 newtons from the x component of the force on the right, and we add the x component of the force on the left, which happens to be negative 86.6 newtons. So the sum of forces equals negative 52.4 newtons. That means that the net force will be pointed leftward. This equals the mass times the acceleration in the x direction, so we can write this equation. Our equation has been set up, and we'll use it in the final step. Now, let's do the y direction. The sum of forces in the y direction is 94 from the vector on the right, and 50 from the vector on the left. And both are positive, because they're both upward, and this results in a positive 144 newtons, which means the net force has an upward direction. We set this equal to the mass times the acceleration in the y component, which is this. We are up to the fifth and final step, using algebra to solve for the quantity that we were asked for. In this case, we were asked for the acceleration of the astronauts, so we are going to want to solve for the acceleration in both the x and y directions, which together form the acceleration vector. Let's start with the x direction. We have this equation, and we just need to solve for a sub x. That means dividing both sides by the mass, which results in the answer of this. We do the same thing for the y direction, divide both sides by the mass, and we get this. Therefore, our resultant acceleration is this vector, which looks like this. So I hope this was helpful for seeing what a force diagram is, how to make one, and how to use it to solve your problem. Force diagrams are a powerful way to solve complicated problems, so long as you follow the 5 steps laid out here.